My name is Sung-Il Kim, majoring in Electrical and Computer Engineering at Auburn University. This summer I had the opportunity to work on FPGA prototyping and software construction for ASIC and USB interface as a part of summer research opportunity program. This presentation will go over the background of the stereo vision, motivation for FPGA prototyping, methodology, results, and conclusions. As you all know, smartphones became very common these days. It can do many things, searching information, taking pictures, and recording videos. Of course, it cannot picture three-dimensional images or videos. Neither it can extract such information from two-dimensional images or videos. But what if machines can do that? What if they can perceive the world like we all do with two eyes? This is known as computer stereo vision. The main difference between human and camera is that we have two eyes. To perceive 3D, we need two eyes working simultaneously. When the two images arrive simultaneously in the back of the brain, they are united into one picture. Our mind combines two images by matching up similarities and adding small differences. That small differences make huge difference, seeing that from 2D. Similarly, for machines, it requires at least two camera lenses, left and right one. From those images, as shown in figure A, it can extract the depth of the images, as shown in figure B. We are developing faster stereo vision hardware Accelerator, which consumes much less power than traditional GPU-based stereo vision. This small chip can open immense applications. For example, since this system can detect the depth, how close objects are in response to a person wearing it can help blind people. Furthermore, biomedical imaging electronics, autonomous driving, robotics require this technology to behave more and more like a human. Also, we can use it to reconstruct 3D objects, as shown in figure C. For application-specific integrated circuits, ASIC, time to market is critical to potential sales. As you see, when the product is released 12 months late, the potential sales drop from 100% to 9%. Furthermore, as process nodes become smaller and smaller, ASIC development cost is rising to several hundreds million dollars. For 20nm technology, the total development cost is $160 million. And interestingly, the proportion of prototype validation is increasing from 65nm to 20nm, indicating the importance of verifying ASIC design before tape-out to ensure its functionality. The following diagram shows data transfer from USB host to FPGA, which is stream in, and FPGA to USB host, which is stream out. This slide shows the interface testing sequence. After ZV stereo camera inputs the load images left and right, software processes them and convert into binary data. Interface programs send binary data to FX3 to test the stream out, and chips code display real-time signals on what FPGA receives. Similarly, FPGA sends the generated data to FX3, and software returns what FX3 receives. The generated output, which shows the depth of the images, can be used for many applications as described earlier. This figure shows the chip scope result for stream out. Flag C and flag D become active whenever FPGA receives the data from FX3, and output enable and read SROP signals respond correctly along with the data received. This figure shows the chip scope result for stream in. Flag A and flag B become active whenever FX3 receives the data from FPGA, and write SROP is active, and other signals including address and feeding data respond correctly. To test protocol that turns the stream in and out mode, interface testing software is implemented, and this figure shows the software flow. First, it detects or tests USB to the host and claims FX3 from the list. After getting the processed binary files from stereo vision raw images, the software determines the length of the data and uses multiple buffers to send the maximum byte allowed. After sending each buffer, it verifies whether the data is transferred correctly and iterates until it finishes transferring. After it finishes, it releases the interface and generates the data file to the host. Here's the illustration of the testing software. Underlying bus and device correspond to FX3. Then endpoints determine the direction of the transfer between FPGA and FX3. FX3 determines maximum packet size, and after its transfer and verification, it displays data transferred. From this interface testing via FPGA prototyping, we verify ASIC interface with FX3 and USB-C. All signals are verified through both interface program and chip scope. Prototype FPGA using Spartan 6 show data transfer of about 450 MHz per second, which is fast enough for the desired performance, and total power consumption of 156 MW. The figure shows the number of sliced registers, lookup tables used, and device utilizations. By prototyping ASIC with FPGA, we can ensure the functionality of the circuit, while software simulation verifies the logics, often it cannot verify in real time. Because stereo vision hardware Accelerator runs in real-time verification is extremely important. This step can reduce chip failure and thus manufacturing cost. Future work includes improving the interface testing for reusability and scalability. As modern FPGA is manufactured with smaller technology nodes, it is possible to test the state-of-the-art ASICs, and the methodology can be improved to reuse the prototype for general data transfer interface in the future. This work was conducted with the support of the University of Michigan Summer Research Opportunity Program. I want to thank Professor David Blau for the research opportunity and guidance through the program. Moreover, I wish to thank Dr. Hoon-Suk Kim and Ji-Yoon Lee for their advising, support, and discussions. Thank you for watching the presentation.